There are a couple of other gas laws, and remember, a law is something that is experimentally observed. A couple of other important gas laws that we need to think about and know about before we delve into a more mathematical discussion of the ideal gas law. One of those, due to Dalton. The legend is that Dalton was a terrible experimentalist. He was actually colorblind, green-red colorblind. Well, as we know, being green-red colorblind does not stop you from being a good experimentalist. And so Dalton actually did some dabbling in the labs, and one of the things with which he dabbled were different gases, mixtures of gases. Now, if we just consider this with an example to start with, okay? Calculate the pressure each of 32 grams of O2, 56 grams of N2, and 28 grams of HE in a 10-litre flask at 293. Well, if we were to just think about the oxygen all by itself, 32 grams of oxygen is 1 mole of O2. So therefore, the pressure of that 1 mole of O2, if we pop it in here, would be 24.1 atmospheres. Go do the calculation. Okay, PV equals nRT. N in this case 1 mole, R because I'm using atmospheres, I'm sorry, and litres, I'm even more sorry. R is 0.08206 litre atmospheres per mole Kelvin, T 293. Okay, and the volume I told you was 10 litres. Pop those in, and you see that if that oxygen was just occupying that volume all by itself, the pressure of the oxygen would be 2.41 atmospheres. But we also have in there some nitrogen, 2 moles of nitrogen. Pop that in, and its pressure is 4.82 atmospheres. Does it make sense that the pressure of the nitrogen is double the pressure of the oxygen? And the answer is yes, because there's twice as many moles of nitrogen as there are of oxygen. And the whole assumption is that the moles of oxygen and the moles of nitrogen have absolutely nothing different between them. It's 1 mole of a gas and 2 moles of a gas. Let's go add on the helium as well. 7 moles of helium, its pressure would be 16.84 atmospheres. Okay, so we've got a mixture of gases that combine to give us a total of 10 moles of gas in there. And by putting in each different gas into the ideal law and calculating what its pressure is, we can see that the pressure of each gas is independent of the other one. And that is a really important concept. For an ideal gas, it doesn't matter what the gas is. 1 mole of gas is the same as 1 mole of any other gas. Now, with that in mind, and in some cases I sometimes think this is a little bit redundant, but we have 10 moles of gas in here. 1/10 of that mole of gas is oxygen. And the pressure of oxygen is equal to 1/10 of the total pressure, which was 24.1 atmospheres. Add all these up, you get 24.1. 1/10 of that 24.1 was due to the oxygen, because 1/10 of the moles of gas in there were oxygen. So you'll see, I hope, that 2/10 of the pressure is due to the nitrogen and 7/10 is due to the helium. Okay, it doesn't matter what the gas is in the ideal gas law, each gas is considered to behave the same. And that is generally a statement of Dalton's law of partial pressures. In a mixture of gases, the partial pressure of each gas, so in other words, in this case, oxygen has a partial pressure, nitrogen has a partial pressure, helium has a partial pressure. The total pressure, which is the sum of all those partial pressures, is the total pressure. Each partial pressure is the total pressure multiplied by the mole fraction of that gas. Put it into a nice little symbolic form. Partial pressure of each gas, so for oxygen 2.41 atmospheres is the total pressure, 24.1 atmospheres, times the mole fraction of the gas that is oxygen. Well, in this case, 1/10 of the whole gas was oxygen, because 1 mole in 10 was oxygen. I think I might have sort of made a little bit of an extraneous meal out of this, but hopefully you've got the idea. The important thing is that the ideal gas law works regardless of what the gas is, and it works regardless of whether it's a pure gas or a mixture of gases, because in the ideal gas law, every single molecule of gas is assumed to be identical to every other molecule of gas. And I hope you start to appreciate the problem that we might start to run into at times with that assumption. Second extra law that we need to think about, associated with a chap called Graham, a Scottish scientist, and both of his laws are associated with the velocity of gases. As a peasant inorganic chemist, I don't actually know why they separate them. But anyway, there are two Graham's laws. One is to do with effusion and one with diffusion. Now, the whole idea is with effusion, you have some gas, you have a hole, the gas escapes through the hole, ideally into a vacuum. Diffusion is where you have two different gases together and they're mixing. So we would have started off with the red and the green in separate ones and they're mixing together. Both are associated with the gases moving. Both of the laws are associated and identical with the velocity of gas. And those laws are that the average velocity of a gas is proportional to 1 over the square root of the molar mass of the gas. Now, we will do quite a lot of examples on this in class because it seems to confuse people generally, no matter how many different ways I say it, so I think it's best to just do examples. But I'll give you a quick example here. Compare methane, CH4, with sulfur dioxide. Methane has a molar mass of 16, sulfur dioxide has a molar mass of 64. So expect methane to be faster. It's the smaller molecule. That shouldn't take too much intuition. The smaller the molecule, the faster it is going to be. What Graham tells us is how much faster. The ratio of the molar masses, right, 16 over 64, or a fourth. So methane is a quarter as heavy as sulfur dioxide. Okay, well, a quarter, take the square root of that, you got a half, and then take 1 over that and you get 2, and so according to Graham, methane molecules will be twice as fast as sulfur dioxide molecules. Now let's take that observation a little bit further, shall we? Consider two different gases, A and B. What we're saying, according to Graham, now make sure you see how I'm doing that, velocity of A over velocity of B. So velocity of A is proportional to 1 over the square root of its molar mass. So if I've got A on top here, square root here, molar mass of A on the bottom. Here I've got in my ratio velocity of gas B. So if it's on the bottom in the velocities, it's going to be on the top in the molar mass side. Everybody see how this goes to that, I trust. Now, get rid of a nasty old square root, so we will square it. So we get velocity of A, velocity of B squared is the non-square rooted ratio of the molar masses. Multiply through, and notice what we've got here. We got the mass of A times velocity of A squared, mass of B, velocity of B squared. Where have you seen before mv squared? Well, I could be really anal and multiply both sides by a half, so it'd be half mv A squared equals a half mv B squared. I'm going to assume you can see those halves in there, and you can say therefore that at a given temperature, the kinetic energy of any gas is equal. Doesn't matter what the gas is, okay? Its kinetic energy is equal, okay? So the faster the gas moves, there is a relationship to its mass. The heavier a gas is, it's going to be slower, and it has this nice relationship. Now, if the kinetic energy of any gas at any given temperature is equal, that means that there must be a relationship between the temperature and the kinetic energy. Okay, and this is a very important result that we will use in the next movie. The kinetic energy of a gas is proportional to its temperature. So anyway, in this first movie, we've reviewed what I hope you saw at A level, the fundamental gas laws, the ABCs, and throwing in G just for fun, taking us to the ideal gas law. You do need to be happy about what I mean when I say SATP and STP. And then we've looked at Dalton's laws and Graham's laws, which I don't know why you don't talk about those at A level, because they are absolutely fundamental in what we're going to be doing next, and talking about what exactly do we mean by an ideal gas, and seeing if we can't apply some nasty little physics to it.